All right, so I'd like to begin this video. Today we're going to talk about the centripetal acceleration, with the goal of this being to derive the formula for the centripetal acceleration. You already have the formula, it's already on your equation sheet. However, I think it's kind of nice, and personally I prefer to know where my formulas are coming from instead of just kind of feeling like, oh, here's a formula, use it, accept it. And so that's what I'm going to try to do here, is I'm going to try to derive that formula in a way that hopefully will make some logical sense to you as well. So we're going to start, and I want to begin this by just imagining some sort of object, and it is undergoing what we call uniform circular motion. So sometimes you will see me abbreviate that as UCM, your book or somewhere on the internet or whatever. But let's just review real quick. So motion means it's moving, circular means it's moving in a circular, and uniform means that its velocity is constant. Not its velocity, but its speed is constant. So it's always got the same speed. It is, of course, changing direction because it's moving in a circle. So I'm going to imagine a yo-yo that is moving in a circle with a radius of r. Okay, and this particular yo-yo, I'm going to draw two different positions of this yo-yo, and I'm going to draw them fairly close together, although not, not infinitely close together, but just fairly close together. And I want to think about, the vector that is between the endpoints of these two, the initial and the final position. Okay, so that vector has a length of change in position, right? So this vector right here is the change in position between the two positions. Okay, and if I wanted to, and I think I will, I'm going to scale it by the time it takes for it to go from position to position. So now it's shorter, I guess. Okay, so as you know, or as you should know, I hope you'll now understand that is the average velocity vector between these two positions, right? So the average velocity vector is just the change in position divided by the time. Okay? Cool. All right, now, I don't really want to be dealing with the average velocity vector. Let's deal with the instantaneous velocity vector. But that's just something that, that we like to think about. So if I wanted to do the instantaneous velocity vectors, well, then I've got a velocity vector at the initial, and then I've got one at the final. Now, notice they've got the same length. And the reason that they have the same length is because they are they have the same speed, right? The direction is slightly different, but they are in different positions, okay? So they're in slightly different directions. All right, now I can go ahead if I wanted to, and I could draw these velocity vectors going all the way around this particular circle, okay? And notice everywhere it's got the same magnitude, so the arrows are the same length. All right, now what I want to get at here, however, is I do want to get at acceleration, right? And so over here on the right somewhere, I want you to remind you that the acceleration is the change in velocity divided by the change in time, okay? So in other words, I have to be able to compare these velocity vectors to each other, the velocity vector at time 1 to velocity vector at time 2. And so what I'm going to do is over here on the right, I'm going to draw my first velocity vector, and I'm just going to draw it as going, where it was. And I'm going to try to make that exactly the same as the one off on the left-hand circle. Okay, cool. So now I'm going to have a velocity vector, the second velocity vector, and we want to note that it is the exact same length because it has the same magnitude, but it's off, it's kind of turned a little bit. Okay? And I want to note, just like in the case of the first, what I did in the first case, I could go ahead and say, okay, well, the average acceleration between position 1 and position 2, well, that's the change in velocity over the change in time. Okay, so I can draw a little arrow that kind of represents that. That's my average acceleration. However, again, I don't really want to deal with average acceleration. I want to deal with instantaneous accelerations. So let's deal with instantaneous accelerations. So the first acceleration is going to be perpendicular to v, and the second acceleration will also be perpendicular to its v, right? And I want to note that if I keep drawing all the v's from the left-hand circle on the right, then what's going to end up happening is I'm going to draw a circle on the left, okay? And at every single one of these, wherever there's a v, there's an acceleration that is perpendicular to that, that v, okay? Cool, right? So now, one thing before I continue is I want to note something about these accelerations that's really, 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 really important. Is that notice that if I look at the first velocity, which is going straight up, okay, that the acceleration is at a right angle to that velocity. In other words, if I go back to my original circle, the velocity is up, but you'll notice that the first acceleration is straight inwards, okay? And if I look at that second arrow, okay, that second velocity vector, notice that its acceleration vector is also straight inwards. So by all of these little A's that I've drawn, if I wanted to, and I will, I'm going to go ahead and draw a little C. That C represents the fact that it is towards the center of the circle. Okay, so that is the word for centripetal. So centripetal just means towards the center. Okay, cool. So now what I want to do is I want to go back, and now we're ready to do some algebra. Okay, so in this first particular circle, I'll notice that I'm moving around the circle at a rate of v. Okay, so v, now that rate needs to equal the distance around that circle divided by the time. So the distance around that circle is 2 pi r divided by the time it takes to go around that circle. Fair enough. Okay, I'm going to use the exact same logic on the right-hand circle, which is that the AC, that's the rate I'm going around that circle, equals. Now the distance around this circle is just like in the first circle it was 2 pi times the radius. This one is 2 pi times the radius, but the radius of this circle is v, okay? And then I'm going to divide it by, it's going to take the same amount of time to go around that circle. Okay, once I have these two formulas, and I believe them, and I've internalized them, and I feel okay about it, what I'm going to do is I'm going to solve for time for both of them, because I don't really care about the time. It's kind of arbitrary anyway, it depends on all the other variables. But so let's rearrange for time. So this one becomes t equals 2 pi r over v, and this one becomes t equals 2 pi v over centripetal acceleration. I could set those two equal to each other, and I get 2 pi r over v equals 2 pi v over ac. The 2 pi's cancel, and if I rearrange, I get ac equals v squared on r. Okay, and that is the formula for centripetal acceleration. So I hope this clarifies things a little bit. It's a little bit quick, but you may rewatch it. So hope you all are well. Okay.